Okay, so we want to visualize nonlinear surfaces. So if I just come up here and change one thing over, maybe I say z equals x squared. This is no longer a plane. We need to change that. This is now a nonlinear surface. And if I want to graph that, I need some other techniques. So the things that are up to this point in the chapter are all how to help you graph linear things. But things get way more interesting when we consider nonlinear surfaces. All right, so let's make some space. And pause that. Okay, now we got a clean whiteboard. We want to graph this z equals x squared in R3. Again, because of the square, we know that's what makes it nonlinear. We're not in the class of planes anymore, so we have to have some new techniques. And maybe the easiest way to explain this first is related to the activity on page 53, is let's look at a simpler one first. Y equals x squared in R3. We'll visualize what this surface looks like, and then we'll be able to work our way back to that one. So y equals x squared, it's going to help us, again, if we think about that in our desktop coordinate system, and draw that back here. So I'm going to erase mine and move my axes a little bit. I always know when I stick a pen anywhere that's the z-axis, so that's obvious. But let's change our axes, shift them a little bit. So I did mine like this. And then I go ahead and graph y equals x squared. Hopefully you know what that looks like. If it's a more complicated thing, you can use the tech tool, calculator, whatever. So we have this shape of the parabola, y equals x squared. Okay, then that's in the xy plane, so I go into the third dimension. Add the z-axis. And so what happens now, this parabola is free, and z takes on any value. This is a copy when z equals 0 in the xy plane, but there's another copy of that parabola just above it at z equals 1. There's another copy at z equals 2. There's another copy at z equals 3. And so what that creates is this half pipe, right, sitting up. So it's a vertical half pipe. And hopefully you see it. That's the most important first step, is make sure you see it in one of your coordinate systems. So we see that. And then we want to graph what we see in 3D on a 2D whiteboard or piece of paper. Okay, so again, as usual, momentarily forget that we're in the third dimension. Turn your head just so. And now you want to graph the y equals x squared in this sort of skewed, turned xy plane. So, okay, negative axes are like this. And so we know that y equals x squared should be a parabola hugging the y-axis. And so what I need to do is draw a parabola that hugs the y-axis, that's sort of midway through this skewed part, and midway through this sort of fatter part. So that is the copy in the xy plane, the z equals 0 copy of the parabola. That is this on this two-dimensional board. So this is the z equals 0 copy of the parabola. But z is free. Didn't say anything about it, so z can take on any value it wants. So I could draw another copy of that, and maybe I'm up here at z equals 3, and I'm going to replicate that exact parabola, just shifting it up 3 units. So it looks something like this. And now it doesn't look like the shape that we saw in front of us when we tilted this, right? So when we were here, we had this sort of half pipe, vertical half pipe sitting in front of us. It doesn't look like it just yet, but just a really easy trick. All you have to do is connect the endpoints. And this back wall here, so that one was a little short. Right. And now you start to see the three-dimensional shape. It is this vertical half pipe. So you can bend a piece of paper and see what that looks like. All right, but again, that was the first nonlinear thing we've drawn, but we really wanted to do the z equals x squared. So let's come back to that one now. Grab z equals x squared in R3. And so the trick with these is that y is free this time. So what I'm going to do is, again, temporarily treat this like the y is ignored for a moment, and I'm just in two-dimensional space. The two-dimensional space I'm in is the zx. But I know what that thing looks like. This is z equals x squared. And now this time, the board actually has the right orientation. I don't need to move anything. This is the y-axis coming out from the board, right? And so that means that when y is free, this parabola gets extended in a half pipe out from the whiteboard. Okay, so you see it in your three-dimensional coordinate system. You see it in front of you. Now we need to do like we did here, draw what we see in front of us in 3D on a 2D piece of paper or whiteboard. So z equals x squared. We have our z and x axes in there. Z equals x squared hugs the positive z axis. So I hug it like this. Should be a little bit more skewed maybe. Like that. That's one copy in the zx plane when y is 0. But we know y is free to take on other values like 1, 2, 3, 4. It doesn't matter what you pick. But what does matter is that you replicate the shape of that parabola precisely. And then connect the ends. And this is the half pipe coming out of this. So we can verbally, we're going to get good at also verbally describing this. This is a half pipe that you could skate in, right? This one was a vertical half pipe. Don't want to skate in that one. Right, and those are your activities then on page, a sample of what you're going to be doing on page 53, 54, 55, and then a really fun one on page 57. You're going to use the book pages to bend them in certain ways to represent certain functions. And there's some nice answers on the next page. All right, so you've gone all the way up to page 59 now in chapter 1. All right, thank you.